Hello, welcome back to EEforEveryone. This is part 12 of the Plant Light project. Today we're going to look at the stumbling blocks that we found while trying to create the Plant Light project. There were a few small issues that compounded on one another, where one of these issues on its own wouldn't have hurt anything one way or the other. Let's start with a small one. In the first iteration of the design, the maximum LED current was set to 500 milliamps instead of 330. This is fine, sort of. Some of the LEDs can handle this peak current, but others are only rated to handle 350 milliamps maximum. Since we learned that the current regulators are pulse width modulating the peak current of 500 milliamps, or whatever it's set to, instead of dynamically changing the steady state set point as a percentage of that maximum, this means that some of the LEDs were being exposed to peak currents higher than their maximum rating. This was not the design intent, and that's not good. Like we talked about in episode 9.5, this was most likely a chair-to-keyboard translation error, and this is what happens when we aren't diligently inspecting the critical sections of every part's datasheet. I'm sure that this behavior, the pulse width modulation of the maximum current, is explicitly called out in the datasheet for that current regulator, and I missed it. In the second iteration of the design, the maximum current was set in hardware to 333 milliamps by changing the current sense resistor from 0.2 ohms to 0.3 ohms. And this lets the RMS current be set to anywhere from 0 to 333 milliamps. Since our set point was 300 to begin with, this current set point is equally valid. This small change fixes the issue. Since the microcontroller is regulating the RMS power to a maximum of 300 milliamps, this wasn't a huge deal, and I didn't notice any issues from the 500 milliamp set point for a few weeks, in fact, which leads to the bigger issue. In the first iteration of the design, the current regulators were fed by the 24 volt input at the barrel jack, and were disabled by transistors that were enabled by the 5 volt rail. So that is, the 5 volt rail biased to transistor, which turns off the current regulators. That's still the topology of the design now. But so that doesn't sound like a big issue, because it doesn't really matter what voltage we're biasing the transistor with as long as it's more than 0.7 volts. But when we first turn on the lamp, the 24 volts is immediately present, but the 5 volt rail hasn't come on yet. During this time, the LEDs were exposed to 500 milliamps of current for a length of time. If the 5 volt rail wouldn't come up ever, they would be exposed to this 500 milliamp overstress indefinitely. This condition would typically only last for a few milliseconds during power-up, but we learned our lesson quickly when we plugged the 24 volt connector into the board and a couple of LED channels popped after flashing briefly. We didn't notice this critical design flaw right away, since we caught it before I received the PCB fabs. Once we noticed, we took care to always plug the barrel jack into the board first when the power supply was discharged, and then plug the power supply into the wall. What this allows for is there's some time when that 24 volt input is ramping from 0 to 24 volts, and this gives the 5 volt rail some time to power up and start regulating to disable the channels before the 24 volt input exceeds the forward voltage of the LEDs. This minimizes the pulse width of that overstress and prevents damage to the LEDs. Now, that workaround didn't save me when I forgot, because I was excited and I plugged the 24 volt power supply into the board after it had already powered up. Now that is when the bright flash followed by the burnt out LEDs is what I experienced. However, if I wouldn't have noticed this flaw before assembling the first board, I likely would have destroyed all of the LEDs on the board before we got any useful data from it. In the first iteration of the design, I also implemented a power latch circuit, which would provide a means for the microcontroller to disable power to itself, and a hardware button to enable the power and latch it on. If one were to have actually used this functionality, then the 5 volt rail would have latched off and we would have cooked all of the LEDs on the board due to the previous two design defects. These three design issues in combination reminded me of some of the things that I already knew, but in my haste to move forward with the project, I ignored my past experience and plowed forward anyways. Let me just reiterate those lessons, so hopefully I won't forget this time. 1. Always design your hardware, so if the hardware or software does the worst possible thing, nothing will be damaged in the circuit. 2. Power supplies don't turn on instantly. You need to plan on the time where your power supplies are ramping from 0 to 100% of their set voltage. Also, if a signal is disabled with a non-ground potential, pull the signal up to the voltage supplying VCC to the circuit. That will prevent any condition where the chip is powered on but the disable is not on. 3. Consider all combinations of the operating modes of the different parts of your circuit. I failed to consider the case when the 5-volt rail was 0 volts and the 24-volt rail was 24 volts. This failure to properly analyze the circuit is the root cause of almost all of these design defects. The best way to mitigate these types of fundamental design issues is to have a peer review the design before purchasing parts or ordering boards. Now, the crew here is pretty light, so I don't have another person to consult for a design review. Given the opportunity, I most certainly would have leveraged a peer review, and this design would have likely only needed one set of boards to be constructed successfully. Thankfully, my big design issues always show up when the board is assembled at the workbench, and the circuit kindly provided its constructive feedback by destroying itself. Once the root cause of this issue was discovered, the mitigations were obvious. 1. Remove the power latch circuitry, since we couldn't use it anyways. 2. Use the board space freed up by removing that power latch circuitry to add reverse polarity protection with a PMOS FET. That way, we won't need a third revision of the PCB if someone plugs in a barrel jack with the wrong polarity. 3. Pull up the disabled transistor for the LED drivers to 24 volts, and add Schottky diodes clamping the control signal to the 5-volt rail to prevent damage to the microcontroller if a transistor fails or is soldered improperly. We'll talk about this more in detail in a future video, where we talk about the protection circuitry on the PlantLight project. 4. Change the feedback resistor for the LED drivers to limit the maximum current to 333 milliamps instead of 500, preventing damage to the LEDs when 100% brightness is requested by the microcontroller. Since these reworks are all on the power board, a second revision is only necessary for one of the two boards. I think it's good to note that while there wasn't any PCB modification required for the control board, the power switch wasn't populated since that wasn't electrically connected to anything after we removed the power latch circuitry on the power board. This leaves two unused pins on the header between the control board and the power board, the one that used to have the switch and the one that used to be used to latch the regulator off. In fact, one of those two unused pins on the control board saves our bacon in part 15 of the PlantLight project. Stay tuned, we have a lot of great videos coming up. Now those are the critical design issues, but from a risk perspective, we still aren't quite done. The PlantLight has no feedback for when LEDs get hot. If the fan were to fail or the heatsink was not installed, we would have no way of knowing. Eventually, the LEDs would fail, or the plastic enclosure would melt, but this could even become a fire hazard, at the very least a burn hazard and a huge mess of molten plastic. Implementing a temperature sensor, or two, on the power board near the LEDs, or using the speed feedback pin of the fans that we're using, at the very least, would be a good fix. It'd give us some feedback to let us know that there's actually a fan installed that's spinning. Though I would prefer the temperature sensing. I wasn't concerned with this issue at the time of the second board spin because I just figured out that my design was eating itself when you plugged it in the wrong way. So we'll have to fix this one with some tacked on wires and elbow grease. Stay tuned for part 15 of this series where we'll implement this change to add temperature control feedback to verify that the fan is actually working. Oh, one more thing. I ordered PCBs that were way too thin for the first spin of the board. If you don't know how big a millimeter is, I'm sorry. This whole design was done in millimeters for no other reason than because I could. Well, that and almost all PCB footprints are specified in millimeters, so it just felt wrong to take a bunch of things in millimeters, convert them to inches, and then, millimeters just felt right. The first PCBs that were ordered were 0.8 millimeters thick. That's 0.031 inches thick. These boards warped a lot. They warped all over the place when trying to solder the LEDs to the board with the hot air gun by hand. Switching to a 1.2 millimeter thick PCB made a world of difference. Not only do the new PCBs not warp during soldering, they also flex less when the heatsink is installed. I mean, they still need the support bracket, but they flex a lot less. Darn, one more last thing. In part 3 of this series, I said something along the lines of, we aren't satisfying the minimum input voltage requirement for the linear regulator, but it should be fine. If you were paying attention in part 10 of this series, you may have noticed that it was in fact not fine. Because our design doesn't satisfy this requirement, the 5-volt output drops to near 4.5 volts when powering the control board. This is plenty high enough for everything running on the board, so I'm inclined to leave it the way it is, but the buck converter could be set to 7 volts and keep the linear regulator operating in its normal region, or you could set that buck converter to 5 volts and just bypass the linear regulator altogether. Since the ripple performance on that 6-volt buck is really, really good, I think that there would be no issues at all just passing that straight to the digital circuitry. Those are most of the mistakes that I have made during the design of the plant light, and all of the mistakes that I've uncovered so far during my testing of this plant light. I relearned a few key lessons about circuit design along the way, and I shared those lessons with you. After all, making mistakes is the best way to learn. Making mistakes on personal projects is great, since the mistakes only impact myself, and the only person I need to answer to is me. Well, you know, me, you, and the whole internet. Please share this video with your friends, so more of the internet can tell me that I'm wrong and learn with us. I'm just happy that none of the design issues were so bad that we needed to throw out the design outright and start over. The tweaks from the first revision of the board to the second were really quite minor. If you think that learning from mistakes is cool and this video is great, let me know by hitting the like button on this video, subscribing to the channel, and leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. Bye!